the general approach of Landau to critical phenomena, but in fact, the reason I'm talking about that is that this approach, it's the way we approach practically any problem in physics. It's the way we approach the standard model of elementary particles, the way we approach hydrodynamics. So it is a completely general approach, and that's what I will try to explain to you. And then we'll find that actually there are serious limitations to this approach. And sometimes, in many important cases, we have to do something better than that. So let me remind you where we stopped. We actually carved the formula outside, but the rain actually extinguished them. There is now completely clean statue there. Let me repeat the logic. The logic was that we started with a concrete model, which by itself is not terribly interesting. It's just the simplest, very crude model of a magnet with the Ising model with variables plus or minus 1. Then we did some transformation. We noticed, though, that there is a miraculous feature in this model, which is Kramer-Swanier symmetry. But then we reduced the model to some field theory. We wrote down the effective action, the action. We wrote down the partition function as an integral over d phi x e to the minus s of phi. And s of phi was some expression like that. Where phi is some field. And then we said that if we go to, so far I'm just repeating what we have been discussing before. We say that if we are interested in the long-range correlations, and that's what happens actually on this lattice, that there is a critical temperature, and near this critical temperature, the correlation length between the spins become infinite. And actually the whole exercise which we are going through is related to the hope, to the justified hope that actually the dynamics in the vicinity of the critical point is universal, that it doesn't depend on minor details. That what does that mean? Let me. I already said things like that, but let me repeat it again to clarify the goal of all these considerations. For example, near the critical point, we measure specific heat. We find that specific heat is divergent. Actually, experimentally, you will find you do with a certain exponent alpha, you will find that the specific heat of the water, for example, actually in reality it was first measured not in the water. The critical point is at very high temperature, so it's inconvenient in argon, and that was very subtle experiments. they were very subtle because you have to not only correlation length in space become large near the critical point, but correlation length in time. So the system relaxes to thermal equilibrium very, very slowly. And one has to be very patient, a very good experimentalist. In any case, people measured this exponent in argon. Immediate question arises. What if it is water, not argon? Suppose we do the experiment. Will it be the same alpha? There are hundreds of other chemical substances with critical point. Do they all have the same alpha? The answer, as we will see, is yes. Moreover, we take a completely different system, the Ising model, a theoretical Ising model. We measure critical exponents in this model, and they again the same. So in a certain class of magnets, critical behavior is the same as in liquid-gas transition, which are physically totally different situations, but nevertheless they have this thing. Of course, it's not the only exponent which is measured. You can also look at the magnetization as a function of magnetic field. There are many things which are characterized by certain exponents, and we will and those exponents as a result of what we will discuss today, it's basically the result of generalized Landau theory, are universal. Not that they're always the same. They depend on the symmetry in question. If you have a magnet with, here we have a magnet with the symmetry phi to minus phi, Z2 symmetry. So this is the Z2 class of universality. If you take, there are magnets in which class of universality is O3, full rotation group, in which order parameter, the magnetization is a vector and things are symmetric. They have different exponents. But again, so there are universality classes characterized, among other things, by symmetries. And inside the universality classes, those exponents are universal. In this sense, they remind me the fact that they are insensitive to the details of interaction. In my mind, there is some mathematical analogy. What do you think in geometry? What kind of things have similar properties? Yes, actually, we have in part of geometry is topologies, and there are topological invariants. There are the simplest one is, for example, is they are expressed as certain integrals, and there are linking number. The degree of linking number is something which measures number of time one contour links around the other, and so on. All these are concrete expressions, concrete integrals which takes integer values most often, sometimes not. But the basic property of topological invariant, we will be dealing with topological invariants later in this course, discussing instantons, which are very tightly related to this. But basic feature, almost a definition of topological invariant, is that under small deformation of geometry, they don't change. And this is somewhat similar to the fact that in the space of all systems, alpha is topological invariant in the sense that if you change the system a little bit, it doesn't change. So you have this interesting analogy. Also, it continues a little further. Namely, in topology, the most efficient way for calculating these topological invariants, like cohomology groups, etc., is algebraic. There's the algebraic topology, which is, it's not that, although it deals with some visual objects like knots or some manifolds with handles or wormholes, etc. The most efficient way turns out to be not to pursue geometrical approach, but to do it algebraically. Something of the same kind we will be discussing in this case. We will start developing today, I hope, the thing called conformal field theory, which is the algebraic method for calculating, sometimes when it works, for calculating those critical exponents. Sometimes we still don't know how to calculate them exactly. And they are also directly measurable objects. So, returning to the Landau theory, the basic point is that we have some effective, the starting point for Landau is to consider, or maybe not, well, to consider free energy as a functional of what is called the order parameter. The order parameter is just generalization, abstractive. It's an abstract version of those spins. So in this Z2 situation, the order parameter will be simply a scalar field, and it's somehow coarse-grained spin. You don't need really exact definition of this. We have the exact definition by looking at this thing. We derived last time that, for example, the green function as a function of momentum is the result which we obtained last time. This is for mu, which is t minus t critical. And we also derived the result that average magnetization or average spin in the Landau approximation is proportional to the square root of t critical minus t. So in this case we already have a critical exponent, but it's kind of a trivial one half. So that's what we obtained this by the mean field theory. Actually, Landau approach is more or less equivalent to the mean field theory. Phi of x is a mean field which appears in the system. You see, we originally started with discrete variables. It was inconvenient, but we, after some mathematical tricks, we passed to the where we are, so we replaced it by some mean field, which is a coarse-grained spin. You can perceive phi as a coarse-grained magnetic field or a spin. It doesn't really matter. What matters is that in this mean field approximation, we get this simple formula, and according to Landau, what we have to do, we have to write down the effective free energy. And then he says, okay, the critical point, all these coefficients so we coarse-grain the system. All these coefficients, they depend on temperature, or if we are in other, they can also depend on pressure. In magnets, it's irrelevant, it's dependence of pressure, but in liquid gas transition, it's very important. There are also critical mixing in which the order parameter could be a concentration of some substance and so on. And we simply obtain the right configuration by minimizing. So we perceive this expression as a classical action, except that it's classical action in imaginary time. And from here, you see that we have a theory with a propagator like that. The propagator like that, and so C2 for a magnet, we assume that it's T minus T critical. When T becomes less than T critical, C2 becomes negative, and the potential energy becomes like that. So we have a non-zero magnetization. Very simple theory, unfortunately not always correct. Now what he says further, that okay, for each universality class we have different order parameters. For example, if we have O3, it should be a vector. If, for a physical example, another physical example, if you have a superconductor, then it was quite a wonderful intuitive prediction by Ginzburg and Landau, that they said that the order parameter should be similar to psi function, namely it should be complex. The only and the free energy is if you have superconductor in the external magnetic field, it has to be gauge invariant. So all you can write, you write the invariant expression plus mu psi square plus g psi to the fourth, and so on. This is Landau expression for, here we have a charge. And now there was an interesting story, because they derived many wonderful predictions about this. They didn't quite realize what is the meaning of psi. But nevertheless, they managed to predict a lot of properties of superconductors. And but when they compared to the experimental data, which were abundant, they noticed that the best description of experimental data will be reached if electric charge E is not equal to the charge of the electron, but it is twice of the charge of the electron. That was just fitting the data. And then Ginzburg said, okay, maybe we have to use effective charge, to which Landau made a wonderful counter-argument. He said it's impossible to have a effective charge, because effective charge would, if you create slightly, by applying pressure, slightly inhomogeneous conditions, then the electric charge, effective charge, will start depending on the point, on the coordinates. But that contradicts gauge invariance. So he insisted that they use the charge of the electron. Now, this is an absolutely brilliant argument, but also absolutely wrong. In fact, indeed, the argument by itself is correct. You cannot have renormalized charge if some effective which depends on x and t and so on. It indeed contradicts gauge invariance. But it is possible that the charge is always constant and equal precisely to the twice charge of the electron. And this is, of course, because superconductivity in superconductors you form Cooper pairs, and the order parameter is actually the wave function. The wave function of the Cooper pairs. Anyway, that's the style, and then you can have more complicated groups. We have phase transition in crystals. You have some discrete crystallographic groups, which are quite complicated, but you always can write down invariant expressions. So that's the Landau philosophy. And then we started after. It's important to understand. By the way, the philosophy, so therefore, is that we deal with coarse-grained order parameter. We keep minimal number of derivatives in the action, and then we decide which terms in the action are important, which are not. So there is always something which can be added. The question is whether it should be added. But already last time we started to dismantle this theory. Namely, we said, let us look at this thing, and we have the green function will contain, there will be this thing, there will be this thing, there will be a diagram like this if I keep phi 4, but nobody tells me there are all kinds of powers of phi. So I will also have diagram like that, and so on. And there are many things which I can add. The question, therefore, is whether these are quantum corrections. They appear, or better to say, fluctuation corrections. In other words, we say that the partition function is this strict. We have to integrate over the order parameter. What Landau theory corresponds to is just taking saddle point approximation to this integral. And then we have to decide when it is legitimate, when it is not. I already made a simple estimate last time. Namely, let's write down the green function. Let's write down the green function in the following way. Where sigma, which is the Dyson representation, and the sigma is one particle irreducible things, like that. And we see that we may get a large correction actually to this expression. Namely, let's look at this integral. Very simple integral. If we are in d dimension, we write down like that. And then I did something last time, which you should have caught me at some. I made an estimate for this integral. I said it's proportional to mu to the power d minus 2 divided by 2. Excuse me?
4. Last time was minus 4.
No, we have to compare it with the 4. you see how I estimate this integral. I get k to the d minus 2. I take the region k of the order of mu, k of the order of square root of mu, and I have k upstairs, and I have d minus k squared downstairs, so the estimate is k d minus 2, and that gives me this expression. But there is a certain cheating here, which can easily be avoided. But first of all, I want you to notice the cheating. It diverges, right? It diverges like if we have a cutoff, we have a divergent of the type lambda d minus 2. Lambda is the momentum cutoff. What does that mean? Nevertheless, I can tell you in advance the estimate which I did. This estimate is the correct one. So you can have, it was the wrong argument which led to the correct answer. And correct answer is the most important things. You see, I never cared whether something is rigorous or non-rigorous. I care whether it's correct or not. You see. Anyway, but let's more seriously, let's make it clean. To make it clean, well, first of all, let's understand what it means. So what does it has significance, this. What does that mean in terms of critical temperatures, free energy, etc.?
I mean, other than the requirement for renormalization?
Well, we don't know such scientific words, renormalization. We will be, but we're just calculating integral. It diverges. We don't know what to do with it. We want to decide what to do with it. Later, we will learn some science and call things renormalization.
Physics depends on little scale.
Yes, but which physics? Actually, it simply means that the critical temperature indeed depends on the small scale. What you said is right, is correct. Physics does depend on a short scale, on a lattice. By the way, I think you can easily answer what should be the size of this cutoff. Why, in fact, of course, there's no divergences here. It's an Ising model. It's plus minus 1. Very simple, everything.
Inverse length of the
lattice. Yes, of course. It's inverse length of the lattice. Right. But what does that mean? It means that the critical temperature is shifted when you include interaction. And indeed, this shift is non-universal. If we don't, mu here was T minus T critical of the zero approximation. You see, now how to, and we want, we kind of expected that if we use this analogy with topological invariance, clearly the critical temperature itself is not topological. It's different. In argon it's one thing, in water it's another thing, and so on. And if you change the chemical substance, it changes. So it's completely an interesting object. Well, it's interesting for some purposes, like in high TC superconductors, for example. But in fact, it's not what interests us now. Now we want to study universal or topological things. And it's very easy to do. As you said, we have to do renormalization, but we do it in a very low key way. We simply write down, we redefine mu and write down the green function. Sigma depends on k and mu, and we simply subtract sigma at 0 and 0. So in other words, what we did, we introduced new mu. Our new definition of mu is shifted by the value of sigma at 0. The reason it's another mu, changed mu. That's what it is. Okay, but why it is convenient to do it this way? So mu nu is mu alt minus sigma at 0, 0. Well, I think it's minus because it's when I... Okay, that's your homework. By the way, we will, Vasya and I will distribute some first homework tomorrow, probably. Anyway, when we write it down this way, mu equals critical point is now at mu equals 0. You see, the problem here was that the critical point is the point where the green function is infinite, or g minus 1 is 0. The critical point was not at mu equals 0, but at mu equals to this thing. And now we did what is the most primitive and simple mass renormalization. After that, you see that this difference between two sigmas is just ddk, k squared plus mu, minus the same thing at mu equals 0. And this divergence happily disappears. It cancels away. But the same thing, the same approach we take, for example, in the standard model. And in the standard model, we have the Higgs field. By the way, the Lagrangian of the standard model should be understood precisely as a particular case of this low energy action, Landau free energy. The Einstein action should be understood in the same way. But in the standard model, returning to the standard model, the Higgs field, which has some reasonable mass, we should be, people are really struggling with it. And it's not clear whether this struggle makes sense or not. Let me explain what I'm talking. I'm talking about what is called the hierarchy problem. The hierarchy problem says the following. Let's formulate it in our language. We have generic action, generic free energy. We don't know where it comes from, but then we should have no fine-tuning of parameters. But if you have no fine-tuning of parameters, we will get the mass of the Higgs field of the order of the cutoff, which is assumed to be the Planck length, some huge energy. In reality, it is the same. It's 125 GeV, which is the same order of magnitude as other particles in the standard model. So you can avoid the problem saying that it's just fine-tuned. In the case of critical phenomena, we know that it's the experimentalist who is fine-tuning temperature to be near critical, and then the mass mass of the scalar field becomes small. So people are struggling with the question: who is this experimentalist in the case of our universe? You see, but it's kind of a philosophical question, because there's no logical contradiction in saying that it's fine-tuned. But so I'm uncertain about whether it's a meaningful question. Maybe yes, but maybe we simply have to reformulate it somehow. In any case, it's useful to understand that the hierarchy problem in the standard model is nothing but tuning up the temperature to the critical value, as we have here. Okay. Now we indeed compare this thing with a term mu here, and we see that we have to compare g minus 1 is k squared plus mu plus some constant mu to the d minus 2 divided by 2. And if you look at these higher diagrams, you will get also the powers of k. You see that if d is equal to 4, these terms are of the same order. But if d is less than 4, by the way, even for d, it's in fact, in this case, this is correction. This correction is important. Now, how to see that? Why do you think I included d equals 4 here? Or why d equals 4, although this naive power-like estimate gives us the same order 1 correction? In fact, it's large. It's large because the integral will be logarithmically divergent. Let's see how it goes. Integral d4k. What? What? No. It's at d equals 2. At d equals 2, you are right, it's logarithmically divergent. But at d equals 2, that's of course, but even at d equals 4, it's logarithmically divergent. Let me see, let me show you how you pick up the logarithm from here. Very simple integral. And d equals 4. And I claim that at dimension 4, if I drop the divergent part, there is obvious quadratically divergent part, but that's this fine-tuning which we already discussed. But what is the next term?
It's also the logarithmically divergent.
Yeah, the simplest way to see it is just differentiate it with respect to mu. You will get logarithm, so it is mu logarithm mu. So it's always small mu, it's always larger than the mean field value. So these are quantum fluctuations which destroy the Landau theory. And what is interesting is that if d is greater than 4, the Landau theory is exact. While if d is less or equal to 4, it should be replaced. Now, let's first understand the meaning of this critical dimension 4. 4 is a critical dimension. There is a, and then we will proceed to the solution of. Let's, since it's important, let's have an alternative way of deriving this critical dimension. You see, we will derive the probability that two curves, suppose we have interaction, the phi-4 interaction, and there is a probability that there is no interaction, and this is probability that there is an interaction. Now, if we are dealing with the ordinary curves, then it's clear that two generic lines always intersect in 2 dimensions. But with random curves, so what I'm trying to say is that with ordinary non-fluctuating curves, we have clearly, if dimension is 2, they generically intersect. This is seen from the fact that if you parameterize the curve, intersection means that x mu of S1, x mu of S2. So you have 2 unknowns and 2 equations which generically have a solution. In 3 dimensions, they generically don't intersect. But fluctuating curves are something like a surface. I shall explain this first to you. And as a result, they intersect in 4 dimensions, and they don't intersect in higher dimensions. So let's make it a little more concrete. By the way, this argument I'm not, let me first explain how to make an estimate. First of all, we know that the amplitude to go from point 0 to point R can be written down as that's more or less the standard thing. We can write down the propagator as a sum over paths connecting 2 points of the terms like e to the minus length of the path. And for this simple propagator, we have a solution of the random walk equation, the heat kernels, and we have to integrate it over this. So this propagator behaves as R to the power d minus 2. It's an important point which I assume you know to some extent, but we will be discussing it also, that in field theory you have 2 representations for a propagator for the free field. One representation is when you integrate over fields and you have the Gaussian integral if you neglect interaction. The other representation is the sum over paths. So there are sum over configurations and sum over fields, and they are equal to each other. Formally, it's proved by checking that this thing satisfies the Klein-Gordon equation. That I assume you know. And if you don't, please ask me. I will be glad. It's more or less standard stuff, which is easy to explain. Now, a slightly less standard stuff. Let's make an estimate. Suppose all those distances are of the same order. We have two green functions here, so this diagram without self-intersections is 1 over r to the power d minus 2 square. And this guy, we have to compare it with this guy. You see, we have now 1 over r d minus 2 to the 4th power, right? We have 4 propagators. And we have an integration r to the d. And you see immediately that critical dimension is 4 from here. If d is equal to 4, I get 1 over r to the 8, r to the 4 here. If d is equal to 4, they are of the same order. If d is greater than 4, in multidimensional space, it's unlikely for the paths to intersect. You see? And so the meaning of critical dimension is that random paths, unlike non-random paths, for non-random paths, the critical dimension is 2, because they intersect in 2 dimensions, and they, generally speaking, don't intersect in higher dimensions. They go like that. With random paths, it's slightly different, and we see that they typically intersect at critical dimension. They intersect with probability of the order of 1, and so interaction becomes important. There is a way to put this argument, a tempting way, but I never was able to make it completely clean.
It's not 4 though.
Huh?
This argument is...
What?
Set it to 4 is not...
Well, let's see. So if d is equal to 4, it should be right, but I could have made a mistake. But let's see. If d is equal to 4, we have 1 over r squared to the 4th power, and we multiply it by r to the 4th. So I get 1 divided by r to the 4th, right? Here I have 1 over r square, so they become of the same order. Okay? Or you meant something else?
No.
Okay. Anyway,
Can you make a similar arguments for strings? For instance?
yes, but it will require about 5 lectures before I do it, before I will be able to do it. But indeed, as talking about strings, implicitly, that I can, the intuitive way of understanding these 4 is the following. When you have a random walk, it actually has effective dimensionality too. When you have, if you have some box of the size r, then the typical random walk will have length of the order of r squared, as we see from this integral. So somehow I would like to be able to give a good, clean argument that it's, and it's called sometimes the Hausdorff dimension. Brownian path has Hausdorff dimension too. And for some reason, it is Hausdorff dimension which matters when we study intersections. But I don't know how to make it a good argument. You think about it, maybe you will come up with some improvement of this naive idea. I believe the idea is correct, but it's, I just don't have a good way to prove it. Anyway, but here is everything is quite clean. You can really write down these integrals and see that my estimates are precise. So we have this situation. Before we go further, one more comment. You see, we come to the conclusion that the free energy of this type can be this plus mu phi square. It can be used as a classical free energy if d is greater than 4. So if you want to solve some problem, it is for d greater than 4. You can use it classically. For d less than 4, you cannot. Now, what it reminds you, what would be the analog, for example? Well, first of all, what do you know about field theory, phi 4 field theory for d greater than 4, for d, say, equal to 5? Begin with what you know about phi 4 theory in d equals 4, and then we will go to beyond 4. So I'm asking something which you definitely know, which you encountered many times in textbooks. What the textbooks say about such theory at d equals 4?
It's renormalizable.
It's renormalizable. And what happens for d greater than 4?
Super renormalizable. No.
So, huh?
It's irrelevant on the IR, right?
Yeah, but you see what it tells us. What it tells us for d greater than 4, we have Feynman diagrams, and they diverge like powers. Roughly speaking, Feynman diagrams are in d equals 4 for renormalizable theory. They have logarithmic divergences, but for this case, it's non-renormalizable, and it has power divergences. Okay, what is the other important non-renormalizable theory? Gravity. Okay. Also power divergences. So and what I'm saying, notice the following interesting thing, that usually it is written in the textbooks that non-renormalization is a very bad thing. We don't, and in a sense it's correct. But on the other hand, notice that it is the only reason why we can use Einstein equations, why we can calculate displacement of Mercury, for example, or bending of light using the Einstein equation. The only reason why it works is that because the Einstein theory is non-renormalizable. If you have you again perceive it as kind of a mean field theory, and you neglect quantum fluctuations. You can neglect fluctuations at large distances only because of non-renormalizability. Now, what is the imagine now that we have, say, quantum chromodynamics or Yang-Mills theory, which is renormalizable. What kind of conclusion? That's well. What we said is the reason that it's completely meaningless to try to solve classical Young-Mills equations in normal time and try to extract some physical information. Why in the Young-Mills theory? Suppose, for example, you can have two charges, and you can easily see that there's a solution of the Young-Mills equation, more or less the same as in electrodynamics, which will tell you that the charges interact according to the Coulomb law. But the moral from the story is that we can use classical equations only when the theory is non-renormalizable. Young-Mills is renormalizable. So what does it mean? What it manifests into? Why? Well, we obviously get the wrong result about the Coulomb interaction of two Young-Mills charges by classically solving. But you can probably add some reason why it happened.
We have to take into account quantum fluctuations in our scales.
Yes. And moreover, we have actually asymptotically free theory in which you have a mass gap. This mass gap tells you that at large distances the theory is totally different from the classical one. It is not really, well, quantum corrections become large at very large distances. And they don't become large in this case. Okay, that's just for you to have the right perspective of these matters. Now let's, yes, go ahead.
Do you imply that non-renormalizability is the condition for the mean field theory to be correct?
Yes.
For this, I don't really understand why. Like for electrodynamics.
Okay, electrodynamics is a slightly different matter, but in fact, because we are in electrodynamics, we have massive electrons. If the electrons were massless, then you also will have trouble at large distances. Now, if like here when we have massless thing, now, but since they are massive, we have two terms in QED. Actually, you asked a very good question. We have Dirac term, and we have modification of quantum. We have quantum fluctuations of electrons, which modify this term. But if Q is much smaller than mass of the electron, it only renormalizes the charge. So effective free energy is still F mu nu squared. It's not the only correct. We do have quantum correction to it. We have 1 over E0 square coefficient here, and we add some constant logarithm of the cutoff divided by the mass of the electron, and that's the physical charge. So in this sense, and this term may be large, and it modifies the original free action. However, this modification is rather trivial, and that allows us, the answer to a question is that we cannot use classical electrodynamics at the distances of the size of the electron. if you are, but when you go beyond the size of the electron effectively drops out, and we have normal electrodynamics. But at the same time, in the young, and there is no photon-photon interaction in electron. In Young-Mills theory, photons interact with photons. It's a good demonstration is that when we have a light ray in a dark room, we see it, but we see it only because light scatters on the dust. We wouldn't see it unless it hits our eyes in a very clean room. Anyway, that's the answer to this question. But now, so far I was very qualitative, and now we have to move forward and make some quantitative progress. The only actually one more. There are still a few things to be said. One more comment. Let's take d equals 4. And as we saw, we have important term phi to the 4th. But can we justify that we dropped the terms phi to the 6th? That's another thing which have to be checked. Whether not only that we have, after all, you see, we had the whole logarithm of Koch in the Ising model, lots of any powers of phi. And nevertheless, I'm saying at d equals 4, this term is important, this term is not. And the way to see it is actually to evaluate this diagram. If you evaluate this diagram, you will see that, or any diagram containing phi to the 6th will be small. Give me a qualitative explanation in terms of paths. Very simple. Why it is likely that this is less relevant than this one. Yeah, it's just you need three-part triple collision for that, for this term to be relevant. And it's clear that triple collision is less relevant. So this is how it is. And another thing which I want you to remember from this discussion, that there is no principal difference between these old dirty magnets and clean modern standard model. A nice clean QCD and is basically the same, follows the same logic.
It seems that Landau theory is quite useless in DS.
Oh, well, you see, it's not useful. Well, first of all, you wouldn't say this if you lived in 5-dimensional space. But actually, let me defend Landau theory. Actually, there are many cases when it's relevant. First of all, in some magnets, you have long-range forces, and they imitate when you do evaluation of various terms, you see that because of these long-range forces, it's in ferroelectrics, you can use the Landau theory. More importantly, this Ginzburg-Landau theory of superconductivity is absolutely correct, because for the following reason, you can evaluate in this Ginzburg-Landau theory I raised, unfortunately, it's basically, by the way, the Ginzburg-Landau theory It's precisely the Higgs model with all, literally, what it describes everything. Now, as I said, it is written in 3 dimensions, and there are large quantum in principle there could be large quantum corrections determined which will modify the free energy. But the parameters are such you can evaluate for real superconductors the value of the coupling constant, and its dimensionless coupling constant is of the order of 10 to the minus 5. So you have a huge domain. Actually, the most important from the experimental point of view is the domain where quantum corrections are simply small. They would become large if you, so in other words, what I'm saying is that you have a formula like that, but which is in principle correct only if t is not too close to t critical. But experimentalists can distinguish only this region. Although people calculated first corrections to Landau theory, but that's interesting, but not really the major thing. The major thing is that in many cases it works, mean field theory works very good because of numerical. It's basically because, well, I shall not go to the dirty details of condensed matter, like there is a ratio between deep high frequency and Fermi energy. They come in a certain combination and so on. So that's the case. And the reason why it works for long-range forces, I already mentioned, is because these long-range forces, well, we started with it because of in the case when there are many contributing factors, long-range, many contributing neighbors, you can use the law of large numbers and you have mean field. So this is how it is. Now let's proceed to, but of course the main challenge is to go beyond the Landau theory. And it's not fully, although some huge progress have been achieved, it's still not a fully solved problem. Let us let's return to the Ising model, and we will discuss both two-dimensional and three-dimensional Ising model and see what it teaches us. It's actually the Ising model, and its exact solution is almost, well, some small miracle is the Kramers-Svanier's duality, which we discussed, but the huge miracle is the Anzeiger solution of this two-dimensional Ising model. Because it was so impossible to predict that it will be solvable. It's impossible to predict that the kind of mathematical apparatus which was needed. It's probably because of that I was told that Landau usually, when he read somebody's work, he was very critical, and he was saying usually that he could do it much better and much faster, which was true, probably. But in case of Anzeiger work, he said, I'm afraid I couldn't do it. And so let me very briefly describe to you in a modern way how this solution is achieved. Anzeiger himself obtained it, in a very complicated way. He actually, I read that he actually described it. He said that he was at Yale during the World War. He had a lot of free time because of the war, and he just started diagonalizing matrices. You can solve a model on 2 by 2 lattice, on 3 by 3, and he said that when he reached, I think, 8 by 8, he started noticing certain. He was simply enjoying diagonalizing matrices. And then he noticed certain trends in the eigenvalues which led to the assumptions. Anyway, how are we doing with time? We first introduce so we are returning to the first two-dimensional, then three-dimensionalizing model, and we will be discussing a new object which turns out to be important both in the Ising model and in field theory in general. That's the order parameter which we already introduced is actually in dual theory becomes what is called a disorder parameter. So let's discuss, and it turns out that the exact solution is possible when you combine correlations of order and disorder parameters. So let me first define the disorder parameter. It's very tightly related to the Kramers-Wanier symmetry. So with Kramers-Wanier, I remind you once more, we have said that we characterize the configuration by if you have certain number of all spins are positive and certain number of spins are negative. We separate the dissident spin by the fence. When I was using this terminology in the Soviet time, it sounded pretty ominous. Now, let's define disorder parameter through its correlation functions. Order parameter we call sigma x, and disorder parameter we will call mu x, and it is located on the size of the dual lattice. So we take this location, and then we take an arbitrary path leading to infinity or to the boundary, and we define mu x as the partition function. Yes, and then we actually reverse the couplings if certain link is crossed by this tail. So we attach a tail to this point. And if a certain link is crossed by this tail, then instead of having say sigma 1, sigma 2, which is the normal if it spins 1 and 2, we replace it by e to the minus beta, sigma 1, sigma 2. So we have a reversed couplings on this link, on this link, on this link, and so on. And we calculate this new partition function, which generally will depend on x and on the path. If we have several mu's, we divide it by the usual partition function. It's a It is an interesting definition. It seems that it's not very practical, but it is. Actually, the best way to understand the solution of the Ising model is through the disorder parameter. Now, first of all, it seems that it depends not on any
What's the second variable? Oh, the
Path.
path. Okay.
path. Yeah, the path. Now, first of all, with this definition, it is path independent. So let's, for example, consider a different path. Then then it becomes this closed path, which contains from the combination of our path and a different path, gives nothing because we can always reverse spins inside. So it is precisely like with the Cramer's contours. So it's path and almost path independent. It will be path dependent. I shall explain it better so you will get used to it. Let's suppose that we have disorder parameter here and some order parameter at some point. And we have a path like that. And now suppose that we move the path so that it crosses this point. We compare this thing with this thing. Then when the tail moves and crosses sigma, it will give a minus. So if you have generally, if you have a don't worry if you don't quite get it at the moment, because the easiest way to get it is to work with it. What's time? Oh, well, we have to. But the last thing which I want to mention here is that does it remove those tails which we attach to the disorder parameter? They should already remind you of some mathematical object. The tails position of which are independent modular possible changes of sign. Do you have any? No, it's not winding number. It's branch points and cuts, 3 in surface. Well, we are getting late, and tomorrow we'll discuss it in details.